Hello. We're about to do combustion theory, and we're going to follow a certain book, Foreman A. Williams' book, Combustion Theory. We're only doing Apex Appendix right now, 3 pages of it, and it's already like very dense. So I need to look at the other sources for things that are very dense in here. So I didn't understand why that happened, so I had to look at other, you know what I mean. So for example, we're going to go fast on some of them, like extensive property and extensive intensive, because I think everyone, I mean, I don't know why we need. I know what they mean, but I never really used that meaning ever. Like I know that intensive means that it doesn't matter about the volume change, like density. I know that a volume is an extensive property because the volume changed, but I never used that fact for any real reason. So I don't really know why this is always like the first thing we get taught, but it does. So there you have it. Like the first thing I teach you is that fact. Why? But I need to teach you that apparently. And then I did, so I did my job on that one. If anyone can explain why that's important, that would be wonderful. But let's just begin. Uh, Zeroth law is always there, right? So zeroth law is basically saying temperature and this mug temperature next to temperature must be that temperature. All right, the environment temperature is really weird. Zeroth law is like a nothing burger. It's like so you say it and you forget about it. I don't really know why it's actually a law sometimes. Anyways, the real law is the first law, and the first law is energy is conserved. Now, what this really means is that energy cannot be created or destroyed, which sounds fundamental, and we know from F equal ma. We're gonna go into F equal ma and figure certain things out by doing that. Because here's the thing: if you go and tell you the equation, which is the heat transfer dq equals to, the differential of the internal energy plus the pressure by the differential of the volume, will you understand? No, I guarantee you, you would just say, "Oh, that's interesting," and move on because you don't understand what's going on. Well, here's what's happening in the molecular level. But first we have to talk about non-molecular level to actually tell you about the molecular level. So let's just go and explain a little bit about this because I'll tell you later on that. Let me just explain this a little bit. This is going to be a lot of statistics. Not a lot, but it's going to be a lot of statistical things. What that means is that math is going to be harder. But with ML and other stuff, because 1 plus 1 equals 2, we all know that. But if you put 1 times 1 equals 1, we all know that. But if you put 1 and 1 in a black box and you say you have a probability of getting a 1 and 2, you're no longer having a definitive answer. And that is hard. And you'll see later on in machine learning and all that stuff when I explain to you guys why that is interesting because you can do a probably distributed function and do it a little bit differently, and you can figure out certain things with that. Okay, so what is force? Force, and another way to say it is this thing over here. So this is impulse, right? Impulse, momentum, right? Momentum is P equal mv, and then if you take a derivative of that, you get ma, right? Now, why do I use that definition? Because you can actually change the mass of it. If you don't know, this implies that force is actually dmv dt. So that gives you dm dtv plus dv dt and I don't think a lot of people tell you this. Well, this is acceleration times mass. That's the F equal ma that you're all used to. And then there is that dm dt times the velocity that not a lot of people really talk about. But to me, I think it's important to always use dp dt definition because I just like it better. I think that's a better definition in my opinion. This is my opinion, and you can just say I'm wrong. This is just my opinion. So what I did over here is F. Now we use the F equal ma version, assuming that the other version, you know what I mean. The when I did the definition where we did what did we did again? F equal dmv dt equal dm dt v. This is very small, and then that goes to zero, which is a very uh everyone does that approximation in mechanics and solid mechanics. In this book over here, I see over here and over here over here. Classic 101 physics. Always explained that way, but that's what we're going to do. And when we do that, we get this form. Now, we can write dx equal to v dt because if we have v, we know that's the derivative of the displacement. So dx equal velocity times dt makes sense in reality. Yeah, that makes sense. Yeah. So when we combine all that, when we move this over here, and then we put this over here, and we put dv dt and multiply by v dt, we get this form over here, which is mv dv. Okay, so with that said, we can take an integral of that and find the work, basically. That's just basically the work. And that is the start of energy. And that's how we kind of start. And when we expand to 3D, basically, is what we see over here. We expand to 3D, we get dx, dy, on fx, fy, fz. And we have our acceleration variables too. We get all that. And instead, we need a dot product, which is the one thing that you haven't really got taught too much that you need, but you do need the dot product. And which does indicate that the integral, if you take over here, is an integral like this, which is a dot product in between, which is a little different, but you generally get the same kind of idea as a velocity square. Makes sense, right? I think it does because if you think about it, v dot v, you're gonna get the magnitude and you're gonna get v square. It makes perfect sense to me. I think we can move on from that. Why did I talk about that? Because we're starting with energy. That's the energy kind of idea. We're going to do index rotation. Index rotation here, when I do VI, that means V dot V. The I's indicate below dot product sometimes. Over here, in the case of summation, I mean, because the dot product is basically a summation reality, so you can kind of make sense why we again have something like this. And when there's like a different kind of summation, I actually put the summation here. So what I'm doing here is imagine myself in an atomic sense. Basically, what I try to say is that there's a bunch of points here, and they have different velocities, all of them, and I sum them all up. Yeah. So we are trying to get the summation of a whole entire group of something. How to explain this in reality is imagine this cup of water, and there's a bunch of molecules, right? Each of them going zip 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 zip, zip with a certain velocity. And I'm summing them all up, and this is why I say particle. So particle doesn't indicate like atoms really. How to explain it is like very small elements. It's basically that. And what we did is basically you got a average vector. So this vector is obviously this vi is obviously some vx, vy, vz. That's all average. So that's like what I did is basically 1 divided by m, and each of these have a summation of m dot v alpha I. You get the point, and it's x, y, and z. They all have that. And with that said, you're just getting the average over here. This average is put in there. And this average is pretty important, and this will give you a lot of ways to prove certain things. And you'll see what I mean sooner or later. So this part over here is like, imagine this profile being the velocity. Now, that's the average velocity, sorry. But the actual velocity is something maybe like this for the particle. I don't know. There's some ups and downs. And this is to indicate all of that stuff. Like the C is just all of that. Just push it in. So this is kind of like turbulence theory, if you know what turbulence theory is. But basically, it's very interesting. Very statistical also. So next we'll do something, we'll just expand this out. This V total will expand it out. We'll get three terms over here. The first term is this, which you can notice that the alpha stays in over here. So what we can do from that is just basically move all the V dot, remember V dot, VI is V squared. So this is actually a magnitude over here. So that's 1/2 V squared. That is true. And as you can see over here, this is a mass. This is a total mass. This is a summation of all the masses. So what that gives me is this form over here. So this is basically saying 1/2 M magnitude of the average velocity squared is the first term. Okay? Now, the second term is interesting. Okay. It looks like it'll be complicated, but it'll turn out to be zero. It'll be nothing. Like a lot of turbulence theory when it's something like this. When if you don't know a lot of turbulence theory, when only thing that matters is when there's multiplication, because multiplication changes everything. But when there's like the loan with another v, it usually turns out to be zero or something like that. And here in this case, it does. So what happened here is we have this, and there's many ways to show it actually. A lot of times they show it with graphs, basically. Hey, if you take an average of this and put it over here and then do all that shenanigans, you can show it. And this is just one way of showing it. When we do the turbulence theory again, because I have his notes, I will show it. Sure, why not? I can show that really easily. When we do turbulence theory. For now, we're not. So we have this, right? We have this. Which is VI, which is the definition over here. We start with this over here. We move this out over here, right? We move the VI because we can, because alpha is all the summation. It does not include the average velocity because that's gone. But if I were to multiply that by m over here, we get this form, right? This form is suspiciously like this, right? So, but let's not claim that yet, actually. Let's not do that yet. Sorry, that's my mistake. We go over here, which we plug in this, right? And then, what did I do here? Okay, so we did that. Here, we expand this. So what I did here is basically, let me just put it over here so you can understand it. I did summation, alpha equal 1, I can just do summation, right? MOVI plus summation, M, MO, sorry, this is alpha, C alpha I. And you can see over here, the first term over here turns to this, which is that. But the second term, but we already discussed that it's originally MV. So already over here, this shit goes to nothing. So what that means is that this must be zero through mathematics alone. There's other ways graphically you can show that if you have this kind of multiplication thing, summation, you must show that it is nothing because you can't have that happen. But in this case, we've shown that multiplying by multiplying the mass with a little bit of the velocity of disturbance equals zero. And if you don't understand why, well, graphically it's basically the disturbance is already average to here. So this line is average, and you already have the summation over here with M CI. So basically the C alpha I will turn into zero when you average them out again, because you already averaged it, and this is a disturbance over here. So that's how it works. But it's really hard to understand because you don't, without the graph. I mean, I can show you by actual example, which probably would be better. Maybe I should make one. The harder thing to actually understand is when VI is a function of time and it's different like this. And then that messes some people up and did mess me up once in the time when before I took turbulence. Or Ada did it. But now I understand what's happening over here. It makes total sense. Um, and mathematically it makes sense too. So there's many ways to look at it, 100 different ways. Actually not 100, but a few different ways that you can look at it and still get to the right answer. So let me just move on to this. From that, you get cut the middle term, right? So what happens is that this term is got cut, leaving these two left die, and left for us to understand because this is where I got confused a long time ago because why isn't so imagine this being this and this being this and this being this. Okay, so K bulk is this portion and K random is this portion. But a long time ago, I mean just today because I was reading his textbook. And it brought back memories. Anyways, why can't we just put K total into it and just be done with it? Right, that was my first question. Now, first, what is total energies first? I mean, we just need to talk about energy. Energy is the bulk and the U with the PE. What does that really mean? The way you need to think about it is that, wait, this is, why is there a double U? Okay, so we can just get rid of that. Um, well, I don't know what happened there. Well, uh, let me double check if I messed up here. Should I pause it? Probably. Because I remember it being exterior velocity plus potential, and okay, I think I was right the first time. Never mind. Maybe. Because this is the definition of internal energy. Internal energy, extensive function called the internal energy. Okay, so this is internal energy. This is the potential energy, and this is the external kinetic energy. Okay, so how do I explain this? Okay, so let me grab a ball or some. I don't know what to grab. Um, let's grab my mug again. So this mug has some potential energy, right? Has some kinetic. So imagine if it's vibrating. This doesn't make sense. Well, yeah. How do I explain this? No, the way I'm explaining it properly is not right. The way I should explain it is like imagine a ball, like just a weird ball, and it's moving this way, and it's vibrating like crazy, but it's still moving this way. So externally, without looking inside, you would tell me that it's moving in this way, like this push this way. Um, and that is kind of what the energy of the bulk is. Now, potential energy is basically if the vibrating ball is on top of a table, something like that. Imagine if it's on top of a table, vibrating on its own. It has potential to go, well, this is, I don't like the table example. So imagine if it's on the top of something falling. It has the potential to fall down, right? That's potential energy, PE. So what is U? U is the internal velocities fighting each other. So you see over here? Here is internal tiny perturbations. There you go. And there we have internal energy. The internal energy actually, a lot of people use lowercase e to denote it. This book uses U, which is totally fine. It doesn't really bother me. Uh, I'm used to E, lowercase e as internal energy because the Dr. Sanchez taught me this one, so I'm used to it and I like it more. But we'll stick with the book convention for now because otherwise I'll confuse myself when I talk about it. So this scalar over here, and this is the scalar because it's an energy, right? It's a scalar. It has to be a scalar. It's a molecular potential bond energy. Now it's not in the textbook, but it is what it is. It is. We're parenting it because I'm 90% sure they're going to talk about something else in here. But I mean, it's not in the textbook actually. Maybe he won't. Maybe I'm the fool. But that's gonna be bond energy. This is extra like chemical reaction. But in ideal case, because the book did talk about ideal and non-ideal, so I'm sure they would. I'm just guessing at this point. Anyways, next portion is basically work equals PV. Now this is I'll explain the next slide because that probably is easier, honestly. Because what about this? Think about what fluid does. Fluids, how does it exert pressure? Work, right? Work is force time distance, right? How does a fluid like show that off? And if you think about it, a fluid will show it off as a form of pressure, most likely, unless you have some other way. Even a chemical reaction, if it's in a piston, right, it will show it off as a pressure, right? I'm trying to think of another way it won't show like pressure, but most likely it would be pressure. So that's why we did PdV as work for now. There could be something else in here, but I couldn't think of anything. And the book definitely did not think of anything because they just put PdV. But theoretically, there could be more additions over here that I don't know about. I don't know what kind of work it would be, but there could be more. Not sure. Genuinely not sure. Oh, electrostatic force. Yeah. Plasma. Yeah. Oh, there could be definitely some other type of work. I just usually exotic. Let's just call it exotic work for now because we're not dealing with that stuff yet. Uh, electromagnetic forces could be there. I didn't even think about that. Okay, so with that said, now we can go over here. So, fun fact, I did not understand for a long time what the book was saying when it was saying like you can get this step to this step. I was like, huh, Where how is this equal? Apparently, what they did was I got this from I finally asked just ChatGPT, and they just gave me equilibrium reversible process is the reason why. And I should have figured it out because they were talking about it like few papers ago that it was talking about that and it was like, oh, that makes sense to why it's equal now. Um, so in general, the second law applies, but we're gonna go for equal instead for some reason. All right. Second law you can prove through statistics again. I forgot how to do it, but my professor I took, Dr. Santillion, taught me once, so it's probably one of my notes. I was looking for it, I couldn't find it, so I don't know where it went, but I'm sure it will one day appear in my head, or I'll spend 6 hours searching for it and I'll figure it out. Again, now, how does this form, right? This is something. Now this is form over here. Honestly, it's just a simple like a multiplication, and you can see it because if you look at this and say ds cancel out, you get temperature, right? So that would mean this makes sense because it's a U and it's a delta U. So it's exact. It's something you learn in exact ODEs when you do those stuff. That's not really special. And what's special is that they add in this term, which is a differential from Ni, which is probably species. It was species, if I remember correctly. Yeah, it was, which is a chemical. They call it chemical potential. Um, yeah, they call it that. It's fine. It's not really bad or good. It's just chemical potential. Now, here's something that is funny. Hemsel function over here. For the longest time, I was trying to make meaning out of this. Don't try. There's no meaning in this. It's just a useful way of denoting U minus TS. Like, there's no meaning. I asked Dr. Sarah in class, like, what's the meaning of these Helmholtz, entropy, and Gibbs equation? Well, I was taking multi-phase. I was auditing it, not really taking it. But he said basically there's no meaning. It's just something that's useful when there's certain things happening. And actually, this should not be here. I put that there because yes, that's the only time I found use in it. But that's probably like 100 different types of use in it. Um, yeah, the book doesn't say that. The book doesn't say this. So I should probably delete that term over there. But basically, very very much just there. I'm gonna upload this to LinkedIn when I'm done. Like all of this thing, all of the stuff. When I'm done with it, go to LinkedIn. Right there. And to be the same thing. Interesting enough, there's one thing I do want to mention to you guys. Do not get fooled. You can't just go to here and to here. People sometimes get fooled by that. You need to plug in this term over here from DU, which is quite common. You do that in the other class too, where when I took a class with Dr. Sanchez. You would need to substitute the E over here, the other stuff over here. I just realized they're not specific, aren't they? Why are they not using Pacific? They should be using DH equal TDS e plus VDP. I usually use that for conversion, but this book does not. That's a little scary. Not really scary, just I never did it that way before. Well, you learn something new. I'm gonna